Welcome to Algebra 2, Section 3.5, Solving Nonlinear Systems. All right, for our introduction, here we've got 6 different systems of equations. Some of the equations are lines, but some of them are not. And you'll notice that none of the equations, or none of the systems of equations, consist of 2 lines being graphed. So what I want you to do is try and piece together some ideas for which graph represents which system of equations, and then see if you can arrive at some solutions. So pause the video and I'll check back in a few seconds. All right, we're back. Let's take a look. Okay, so letter A, we've got y equals x squared as one of our functions, and y equals x plus 2. Instantly, we should pair that set of equations with capital A here, this graph. And it's pretty easy to spot because y equals x squared, that's our basic parent function parabola, and that red graph in capital A here is the only one that shows that. Now our solutions are going to be where those graphs intersect. So here we've got the point -1, 1 and the point 2, 4. All right, for letter B, here we've got another parabola and the other x plus 2 line. So the other x plus 2 line, I notice that's in E, so that goes with system B from up above. And the solution points here, where those graphs intersect, we've got -2, 0, and we've got the point 2, 4 again. Okay, so we've got that one handled. Letter C, x squared minus 2x minus 5. Okay, so I know that has a y-intercept of -5. That could be helpful. And also we've got another line, -x plus 1. Well, here's our only negative sloping line. There's our y-intercept on the parabola of -5. That must go along with system C. Okay, our solution points here, we've got -2, 3. And then we've got 3, -2. All right, for D, here we've got one parabola opening up and the other parabola, the perfect opposite of it, opening down. Well, it looks like it's between graph B and graph C here for that. Let's see what -b over 2a gives us. -1 over 2, -1/2 for an axis of symmetry. It has to be graph B. All right, our solution points there. Based on the graph, it looks like we have -1 1/2, or -3/2, 0. And then we've got 1, 0. All right, for system E, x squared minus 2x plus 1, -x squared plus 2x minus 1. Again, they're perfect negations of one another. That means they're a perfect vertical flip. The only one of those left is graph C. And the points of intersection, just one point, the point 1, 0. And that leaves us using the process of elimination that system F goes with graph D, and we've got solution points -1, 0, and then it looks like 1/2 oh boy, that's not very easy to spot. 1/2 and then 2 1/4. Wow, that one's tricky. And that's just an estimation based on the graph. We're still looking for points of intersection. That's the main thing to take away from this little introduction. All right, our key concepts for today. So the methods we covered in Chapter 1 for solving systems were graphing, substitute, or eliminate. And we can also use these when solving systems where the equations are not linear. We just need to be careful if we're using elimination that we don't combine like an x squared and an x term. So there are some little little nuances here. When we substitute, if we have y equals something and we're plugging that into y squared, we may have to FOIL. So it's a little bit more involved, but the general process is really exactly what we would expect it to be. And as we saw in the introduction, we're still looking for where the graphs intersect, although now we could have different types of solutions. It's not just going to be 1 point, no points, or infinitely many. Here we could also have 2 solutions, and you can see it just deals with the bending of some of those graphs. All right, our first example, solve using the graph. Well, number 12, that's about as easy as you can get. Those graphs do not intersect, therefore there is no solution to that problem. Number 14, here it looks like we have the point. Oh, look at our graph, it's going by 2s. 2, 4, so negative 4, 0. And then that would make this 1, and up at a height of 5, so the point 1, 5. That's kind of sneaky on their part. You notice that the x-axis is counting by 2s, and the y-axis is counting by 1s. So this point right here, it looks like it should be 1/2 5, but it's actually 1, 5. I like that. That's good. Example 2 here, solved by substitution. In number 16, they have blessed us with this second equation that says y equals 7 minus x. So I'm going to plug that in to the equation up above. So I've got x squared plus, not y, but all of 7 minus x, that quantity squared, equaling 49. And by substituting, now you see x is the only variable that I have. X squared plus, here's where that nice little shortcut we covered earlier works well. 49 minus 14x plus x squared equals 49. If we combine like terms, 2x squared minus 14x equals 0. All right, well, here this is an easy factoring problem, right? We can't use square roots because we do have a regular x there. But if I factor out a 2x, I'm left with x minus 7. And that tells me that x could equal 0. That's coming out of this loose factor that really means x minus 0. Or x could equal positive 7. So I know I've got 2 answers. One is 0 comma something. The other is 7 comma something. Our answers should be solution points again. Points of intersection. And if x equals 0, then y equals, well, look at this nice equation we have that'll tell us what y equals. Y equals 7 minus 0. And in the other equation, if x equals 7, then y equals 7 minus 7. So we have 2 points of intersection there, as shown. For 22, this looks horrendous, like horrible. I couldn't decide on the word there. But really, the substitution is not terrible. If you'll notice, they've told us what 4x squared is equal to. Well, there's a 4x squared right down here. So let's take all of this y plus 16x minus 22 and substitute that in. So y plus 16x minus 22, and then continue on with our second equation, minus 24x plus 26 plus y equals 0. All right, if we combine like terms, I've got 2y, I've got 42, I'm sorry, I do not have 42. Erase. I apologize, this is probably killing you that it's going so slow, but I'm trying a tablet instead of a smart board to see how that works. My x terms, okay, we've already handled the y's. I got 16x and negative 24x, so that's negative 8x. All right, got those taken care of. Negative 22, positive 26, that's plus 4 equals 0. Okay, and Let's see what we come up with further. Oh, this might require repeated substitution. So here we've got 2i. Let's solve for the y in this case. If I add 8x over to the other side, subtract away the 4, and divide everything by 2, I find that y equals 4x minus 2. So that's what I get by substitution. Well, now I can take this expression here and in turn substitute that back into one of the equations up above. I'll choose the top one since it has a nice y to work with. So I got 4x minus 2 plus 16x minus 22 equals 4x squared. Yikes. If we get this situated, we can see the trinomial forming. We've got x squared, we've got regular x's. So let's combine like terms, and let's move everything over with this nice positive 4x squared. Get it set equal to 0. So I got that 4x squared. This is going to be positive 20x that I will subtract over, so minus 20x when I move all of that over to the right-hand side. And then I've got negative 24 that I will add over to the other side. So plus 24 equals 0. All right, now I notice that I can divide both sides of this equation by 4. I will definitely do that. And now it is factorable. So I've got x minus 2, x minus 3, and I find my x values could equal positive 2 or positive 3. Well, let's see what the y values are. We've got a nice place to substitute those. So I've got the 0.2 something and the 0.3 something. If I plug in that 2, y equals 8 minus 2, 6. And if I plug in my 3, y equals 12 minus 2, 10. So that one required multiple substitutions, and you know what? I'm not entirely sold on that. So let's just see what happens when we actually do graph both of those equations. I'll pull up my calculator, and I'm just going to graph both of these as if they were y equals something. So in the y equals menu, let's clear out the garbage that we have in there already. If I wanted this first equation to be y equals something, then I would simply have my 4x squared on the right-hand side. I would subtract over the 16x, and I would add over the 22. For the second equation, I want to subtract everything else away from y, so I would have negative 4x squared. As always, if you ever get a syntax error, check to see that you might have accidentally hit the minus sign instead of the negative sign. Those are different keys on the calculator. So that's another. Sometimes people think they're doing something completely wrong when it's just a little slip up like that. I would have a positive 24x, let's keep going, and I would have a negative 26, or minus 26, I should say. And if I graph those, you can see, sure enough, those two graphs do cross at what appears to be the 0.26 and then at the 0.310. So the fact that we got two solutions for that, it fits with what the graphs are showing us. Clear those out for next time. All right, next examples, let's solve by elimination this time. All right, so number 30, here this actually would not be a bad candidate for substitution as well. Since they're both equal to y, we could just set those two expressions of x equal to one another. But the y's are also set up beautifully to eliminate. All I need to do is multiply the top equation by -1, and then when I combine those together, I find that 0 equals 4x squared plus 24x plus 32. I can divide both sides by 4. Whenever we catch that, that's a nice way of cleaning this up. And now it is factorable. I got plus 4 and plus 2. So I know that x equals either -4 or -2. So -4 something, -2 something. And I've got two places where I could substitute in and find out what y is equal to. I'll use this bottom one since I haven't changed the signs on everything. If I plug in a -4, I get 3 times -4 squared. That's 3 times 16, 48. plus 18 times negative 4. 18 times negative 4 is negative 72, plus 22. Well, that's 48, and negative 50, that's a negative 2. Let's see what happens when we plug in a negative 2. What's our output there? 3 times negative 2 squared is positive 12, plus 18 times negative 2, that's minus 36, plus 22. So I've got, what, a negative 24 and a positive 22, negative 2. And again, this one is beautifully set up to check in our calculator. We could just type in this equation as y1, the second equation as y2. We have to use the originals, but we could check our work and make sure that those points are the intersection points. All right, number 32. Here, again, the y's are set up, this is even better than the last one, set up perfectly to eliminate. I'm going to go ahead and combine. Y and negative y, those are like terms. They combine to make 0. I've got x squared and no x squareds in the bottom equation. So it's like x squared plus 0 when I combine. 4x and another 4x is 8x. 7 and 7 is, of course, 14. Okay. Well, here, this is one that's not easily factorable. That doesn't mean the problem is unsolvable by any means, but we just have to resort on some different solving techniques. So if it's not factorable, I can't use the square root property, we're going to try quadratic formula. So x equals opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. Oh boy. So we are going to get some real solutions here. They're not going to be pretty, but they will definitely work. So let's see, x equals negative 8 plus or minus the square root of 64 minus, let's see, that's going to be 56 all over 2, which means my x values are negative 8 plus or minus the square root of 8 over 2. Negative 8 plus or minus, if we simplify that radical, 8 is 2 root 2. That's a nice one to remember. So I've got negative 4 plus or minus root 2. All right, so let's see what we get. I've got negative 4 plus root 2 comma something and negative 4 minus root 2 comma something. And this is probably overkill. I imagine they want us to use our calculator here. But let's see if we can't do this by hand and prove that we're superior to the textbook. So here, the second equation, I'm going to rewrite that as y equals negative 4x minus 7. Just multiply both sides by negative 1. That way I'll get a nice clean output for y. So for this first case, negative 4 plus root 2, y is going to equal negative 4 times negative 4 plus root 2, and then minus 7. That means y equals 16 minus 4 root 2 minus 7. So my y, when I combine like terms, is 9 minus 4 root 2. And that's an exact answer. Of course, we could get decimals pretty easily from our calculator to go along with that. Let's see what happens when we do negative 4 minus root 2. So I got negative 4 times negative 4 minus root 2 minus 7. We're seeing a lot of the same steps here, 16, except now it's plus 4 root 2 minus 7. That result, when we combine like terms, 9 plus 4 root 2. And if we got decimals, we could check those in our calculator. In fact, later this lesson, we're going to talk about how you can use your calculator to greatly very accurately check your work with these two. Example 4, solve the system using any method. Well, here the first equation they've given us is perfectly in terms of y. So that is screaming substitution at me, because I've got a place where I could substitute that in directly into the second equation. Also, I noticed that if I wanted to eliminate any of the other variables, there'd be a lot of rearranging and also adjusting the equations. We could use elimination and maybe try and set up a case where we have negative y in the second equation, but the substitution just really jumps off when we see y equals. So we substitute that in, we got negative 3x squared plus y. So I'm adding in all of this quantity. I'll just put that in parentheses for now. I know those signs won't change, but if this were a minus y, I want to be sure that I would see that distribution if I needed it. So negative 3x squared plus what y is equal to, let's finish that up, plus 12x equals 17. Negative 3x squared minus 4x squared minus 16x minus 13 plus another 12x equals 17. Okay, we can see the trinomial forming. We've got x squareds, we've got regular x's, and we've got constants in there. If we combine like terms, negative 7x squared minus 4x, and then I'm going to subtract the 17 over, so minus 30, 30 equals 0. I cannot divide all three pieces of this trinomial by the same number, which is unfortunate, but I can divide both sides by negative 1. Okay, we're treating both sides of that equation and keeping it balanced. All right, 7 times 30 is 210. And I'm not sure if there are factors of 210 that have a sum of 4. So let's use our quadratic formula and see if we come up with something here. If it's not easily factorable, it's much faster just to resort to quadratic formula. So opposite of b plus or minus the square root of b squared minus 4 times a times c. Well, that's going to end up being 120 times 7, 840, all over 2 times a. And you can see our discriminant tucked underneath there is definitely going to end up being negative. So we will have no solutions there. If our x value is imaginary, we're not going to be able to find a y value to go with it. All that work for no solutions. Example 5, use your calculator to solve the equation by graphing. I would put quite a few stars next to this. This is the one thing in math that I refer to as a life hack, because this applies to virtually any situation that you want to solve an equation. We've got two sides to this equation, and you can see each one is its own quadratic function. And yeah, we could divide both sides by 2, and I'm sure we could do some damage algebraically. But if we have this left side be its own function y1 in our calculator, and the right side be another function y2 in our calculator, then we can use the definition of like these systems of equations, their solutions, and we can find out where they intersect. And the calculator, again, just does a fantastic job of this. So I pull up that calculator. Under y1, let's type in our 2x squared minus 12x minus 16. Again, I'm not even bothering to simplify that. The calculator is going to do all the work here. Then we've got negative 6x squared plus 60x minus 144. Okay, now I know that these are two parabolas, so they could intersect once, twice, or not at all. They're not the same exact equation, so it won't be infinitely many solutions, but let's see what we see on our calculator screen. So it looks like they're going to intersect twice, but I can't fit that on the window. So what I need is to look down here in quadrant 4. I need to adjust that window to fit what we need. So for x min, I'm going to change that to -1. Just because nothing was happening off to the left, we're not as concerned about that going all the way to -10. For x max, I'll leave that as 10. It looked like my intersections were going to fit on the right side of the screen as it was. For my y minimum, I need to go lower. So I'm going to make this negative 25, and I'll have it go up to a height of, I don't know, I could leave that 10. Let's just try 5. But now let's see what our graph looks like. We still can't see both intersections. It certainly looks a lot clearer when we see one intersection but not the other. So let's go back into our window. We need our y minimum to go much lower. Let's go negative 40. And there we can see both intersections. It is just a matter of guess and check, but we want to see any intersection points on the screen for us. So in that calculate menu that we've used for values and zeros so far, you can also use it for minimums and maximums, which is a nice way to check our vertex work that you often have to do. Option 5 is intersect. Okay, so it's looking for an intersection. It's asking what's the first curve, and you can see it has a cursor on the first graph that we typed in. So we'll hit enter. Yes, that's our first curve. The second curve, yeah, it's kind of hidden up here, but they have the cursor on that second graph we typed in. So we'll hit enter, and you'll see there are 2 different intersections. It's asking for a guess, so we want to toggle over until we're close to one of the intersections and hit enter. So you can see 2.438 and negative 33.369. Those are the coordinates of that first intersection point. That's our first solution, the whole ordered pair, to this problem. Now we'll run through the same process again. Calc, intersect, first curve, second curve. Now I'm going to toggle to the right with my guess until I'm close to that intersection. I'll hit enter, and you can see it snaps to that one. 6.561 and negative 8.630. So those are the coordinates of that second intersection point. So the calculator does a fantastic job of this. Really hang on to this principle because it works not only for polynomials that we want to match up, but exponentials and logarithms and a lot of the complicated things we're going to talk about later this year. It's an excellent thing to fall back on, and an excellent strategy to fall back on if you have no idea how to solve the equation. Example 6, our word problem here. The range in miles of a broadcast signal from a radio tower is bounded by the circle x squared plus y squared equals 1,620. A straight highway follows the path of y equals negative 1/3 x plus 30. For how many miles along the highway are cars able to receive the broadcast signal? Now you may remember from geometry that first equation is a circle centered around the origin, and then this negative 1/3 x plus 30 is a line that's traveling with a negative slope, and this isn't an exact graph, but I'm just trying to get an idea of the situation. We're trying to find the distance of that, to use a geometry term, of that chord where the circle has the line passing through it. Well, in order to find that length, we need to know the coordinates of those 2 points where the circle is intersected by the line. This is a good candidate for substitution, and really it's about the only way of doing this problem without having a bunch of extra work involved. We're going to go through this by hand. We could possibly do the life hack method. It's a little bit tougher when we have y squared. There's a little bit more to consider, but let's see what happens doing this by hand. I see this as kind of a challenge. So if we substitute negative 1/3 x plus 30 in for y squared, I get x squared plus negative 1/3 x plus 30, that's what y is, it's got to be squared, equaling 1620. X squared plus, here's a nice, we have to FOIL this out, but if you know that nice little shortcut that we talked about earlier, we pretty quickly get 1/9 x squared minus 20x plus 900. Let's combine like terms and get it set equal to 0. 10/9 x squared minus 20x. If I subtract over 1620, then what I get is negative 720 equals 0. And I know this looks brutal to work with. We can actually divide both sides of this equation by 10. If I divide that by 10, instead of 10/9, I only have 1/9 x squared minus 2x minus 72 equals 0. All right, now that we've got this simplified, we can actually see if it factors. I know that 1/9 is kind of scary. We can multiply both sides by 9, but that would make these numbers outrageous. So let's just try and work with this 1/9. That's kind of cool. So 1/9 times negative 72 is negative 8. What multiplies to be negative 8 and adds up to negative 2? Well, negative 4 and positive 2. We've got to divide by the a term, so I've got to divide by 1/9. And then simplify that, clean it up. I get negative 36, and I get positive 18. So that tells me that my factors are x minus 36 and x plus 18 that equals 0. Okay, and I realize that this doesn't FOIL back to what we started with, but remember, it's scaled up so as to eliminate the 1/9. Even though it doesn't FOIL back, we're still getting the same zeros out of it. All right, so what's that telling me? One point of intersection is 36 something. The other one is negative 18 something. And we have this lovely negative 1/3 x plus 30 that we can use to find the y values that go with it. So for the 36, the y is going to equal negative 1/3 times 36 plus 30. Well, that's negative 12 plus 30, that's 18. And for the other one, I've got negative 1/3 times negative 18 plus 30. That's a positive 6 plus 30, 36. Okay, so we found the 2 points where that radio station first is received by the car, and then another point later on where the car leaves that station's signal. So we need to find the distance between those 2 points. Well, let's see. I've got x2 minus x1, negative 18 minus 36 squared, plus y2 minus y1, 36 minus 18 squared. All right, if we simplify that, inside I've got negative 54 squared. And the second quantity, I've got 18 squared. 54 squared plus 18 squared, I just kind of worked this out on paper, is 3240. And then if we wanted to clean that up using a factor tree, just to save space, I'll leave that work to you if you wanted an exact answer. We get 18 root 10. And then from our calculator, we could have done this calculator step way back here, but that distance is 56.92 miles. So kind of stuck it to the textbook there and did all the work by hand. Always kind of a rewarding feeling when you accomplish a really tough problem by hand. But again, a lot of this work could have been done by a calculator. We could have used quadratic formula here to make our workload a little bit easier. And we may have done that. And then as soon as we set up the distance formula, we could have our calculator do all that work. So really nice problem, though. I really like that one. Here's a look at your assignment for section 3.5.